Hello, everyone. I'm going to be presenting on behalf of my team the LATAM high-level synthesis. It's about the FPGA firmware design and verification for the ATLAS Liquid Argon Calorimeter trigger processor. Here's the agenda of this presentation. I'll do a quick motivation talk. I will explain a bit about our designing flow, and I bring some designing examples, and then I'll go to the conclusions. Oh. Okay, better now. Okay. Yeah. Okay. It's good now? No. I want me to get the microphone.
You want to try the mic?
Yeah. Okay. We have here the LATAM block diagram for the LAR backend firmware that is currently running at 0.1. And this firmware was implemented using time division multiplexing logic. And the time enclosure for this firmware is really challenging, and the area utilization is high. So we did some exploration studies, and we found that we can improve the overall designing by using a new architecture, focusing on parallel logic and design abstraction based on high-level synthesis. This way, we can improve the logic usage, the latency. We can get better time enclosure, design verification. And also, one advantage of using high-level synthesis is that we can do easily the results sharing because the high-level synthesis tools does this automatically for us. So we decided to redesign two of these blocks, the remapping and the output summing, focusing on reducing the total area utilization by routing the data more efficiently, because this allows us to reduce the number of the filtering blocks, and these filtering blocks, they use mostly of the area of the FPGA. And also, this is for learning more about leveraging the parallelization versus the serializations for our cases, and to test if the high-level synthesis can be beneficial for future detector upgrades. So here we have an overview of the LATAM high-level synthesis designing flow. We are using Eclipse in the first stage to do the C++ coding. Here we can do quick simulations and test the functionality of our blocks. And after everything is working well in this first stage, we go to the second one when we use the Siemens Catapult to convert this C++ code into RTL. And here we can use the same test bench from the previous stage to do the RTL simulation. And in this stage, we also do the estimations for frequency, latency, area, and the implementation trade-offs, because you can choose it to focus more in the latency, in the area, in the frequency. So when everything is working well in this second stage, we go to the last one using Quartus priming for the final RTL characterization. Here we use the Design Explorer to validate the area and the frequency. And more details about this design flow were presented by Marcos in this reference. Okay, so the first example I want to talk about is about the switch matrices. The LATAM boards, each one of them receives data from the detector for 48 optical fibers, and this data is transferred from 8 sensors using time division multiplexer interfaces. And this original design keeps this time division, this TDM interfaces, and routes the data to the respective filtering blocks in multiple steps. But the idea for this new architecture is convert this data from serial to parallel and routes it to the filtering blocks in one single step implementation using a switch matrix. So in this first figure here, we can see a full mesh switch matrix example where all the inputs are connected to all the outputs, but for implementing this way, we would require more than the 100% of the FPGA area. Is not possible. So we did some analysis for our 116 boards, and we found that we can connect only the necessary inputs and outputs. And in this way, we're using a sparse switch matrix. We only require to use 4% of the FPGA area. So this implementation is comparable. There's an area comparable to the previous solution, and it has half of the latency, less than half of the latency of the previous one. The second example is about recurrent operations, because we have this multilinear encoding operation that must be repeated 320 times. So to implement this block, we created it using high-level synthesis as if we were to use all the design in parallel, like one block per input. And then after the implementation of one block, we could decide what kind of resource sharing to use. So we could use the high-level synthesis tool to decide, for example, not to use a resource sharing, so 320 blocks, and the latency is 5, the area is 4.5% of the FPGA. And then with one single click in the button in the high-level synthesis tool, we could decide to use 64 blocks to share these resources. So the latency increased to 9, and the area decreased in 40%. And we tried also to use 48 blocks. The latency increased, and the area also increased. So we decided to use this second option. And it's important to highlight that even in a later stage of the project, we can trade this area by latency without changing any source code, only going to the high-level synthesis tool and configuring how many blocks we want to share. Okay, the third example is about expensive operations, because we were not able to find the primitives to implement our large multiplexers to be able to run up to 280 megahertz. So we had to decompose a single expensive operation into multiple cheaper operations. I have here this example. This large multiplexer with n inputs was decomposed in n-1 two input multiplexers to be able to run in our clock frequency. And the last example about clock retargeting. In the later stage of our design, we noticed when we are putting all the blocks together that the switch matrix was failing to complete the time enclosure. And it was due to this first figure here, solution A. A lot of operations was done in only one clock cycle. So in order to improve this time enclosure, we retarget the high-level synthesis design clock frequency to reschedule this in some pipeline stage, like do these operations in more clock cycles. This way, we could improve the time enclosure, and the price was to get a higher latency for our design. So here we can show that it's possible to exchange frequency by latency, and this is done without changing any line of the code, the source code, only by changing the parameters in the high-level synthesis tool. So just a summary, this study is still in progress, but we have learned some lessons. The first one is that to use it, the TDM is a bit complex, so in some cases it's better to deserialize this data to process it in parallel. Also, we learned that we can trade error by latency by exploring different resource sharing options, and this is done automatically for the high-level synthesis tool, so you don't need to change any source code. We also learned that sometimes using a block multiple times will not give us the better area, like in the example of the multiplexer, or the multilinear encoder in the case, that sometimes you get less blocks, but the area is bigger, because to share this resource, it increases a bit the logic. And also, we learned that sometimes we need to decompose a large task to multiple smaller ones to be able to run in the desired frequency. And we can trade the frequency by latency by retargeting the clock in the high-level synthesis tool. And this can be done without changing any line of the source code. It's automatic by the tool. So, thank you.
Thank you very much, Melissa. Just before the questions, I remind you to get your, there are some badges here. Some people didn't get their badges, so don't forget that. So since we're running very late, maybe 1 or 2 questions max. All right. Maybe try this one now.
Yeah. So on slide 6, you said something along the lines of, with just one click, we went from 320 blocks to 64 blocks.
Yes.
But I noticed that the throughput goes from 1 to 5,
yes,
which means that the same block can't handle the next data for 5 clock cycles. Isn't that a problem? Is that all right?
No, in our case, we could afford this one. Yes, it was okay, but it's true, the throughput increases.
Okay.
Yes.
Thank you.
Seems there are no other questions, so let's thank the speaker again and see you at the coffee break.